a series of 3 lectures, and the title of the series of these lectures is Optimization and Data Science. But he's going to decide what he's going to talk on.
Wonderful.
And today I think it will be more introductory. And over to Venkat, because I don't want to waste Venkat's time.
No.
Please go ahead.
Thank you.
Thank you.
Good. I've planned 3 lectures. The first one is very tutorial, mostly background. How many of us know linear algebra? Good. There is a question in the talk about linear algebra, so we will see how many people know linear algebra. How many of us know optimization? How many of us have heard of convex optimization? Good, some fraction. So hopefully, for some of you who've seen convex optimization, this will feel like a bit of a review. But even then, maybe there is something in the perspective here that is a little bit different. But okay. So if you've not seen convex optimization, perfectly fine too. Like I said, this whole lecture is completely tutorial in nature. So we'll build up really from very basic things all the way to some cutting edge topics in optimization. We'll do that today. And then the next 2 lectures will be on more current research directions, topics, and so on. Okay. Again, please feel free to stop me at any time. So if you had to ask what is optimization, and you had to, if you open up the dictionary and look up the definition, right? It will say something like this. It is about identifying the best thing from some collection of things, and where the notion of best, is specified according to some criterion, right? The oldest applications of optimization, the first place where it came up in where it was used outside of just being a mathematical discipline, was actually in science. So we all know of Newton's laws and so forth from the 1700s. But subsequently, so late 1700s, 1800s especially, a big intellectual effort in science, particularly in physics, was to be able to write down laws as the solution of optimization problems. So, if you've taken a class beyond introductory courses in physics, you will have heard of things like the principle of least action, principle of maximum entropy. This one goes to the 1800s. This is very much a 1900s principle from thermodynamics. And in these areas in science, one wrote down laws, things like F equals ma and so on, as the solution of optimization problems. It was believed that nature inevitably wishes to solve optimization problems. That's how laws of nature arise. And that was, if you will, the first big intellectual application of optimization ideas. Okay? And of course, now we've all seen significant engineering applications, especially in the 20th century onwards. And a big feature of these applications over the past 100 years or so is the role of computation. Okay, is the role that algorithms have played in optimization. So before the sort of recent trend, algorithms were not really a part of how optimization was applied in scientific contexts, but it increasingly has become a significant part of optimization, say over the last 100 years or so. Okay. All right, so what does it mean to solve a problem? Optimization is now a toolbox to try to solve problems. What does it mean to solve a problem? When you first learned how to solve a problem in middle school, right? Algebra, linear equations. I met somebody in 6th grade yesterday, and in Math 1, Math 2, they were doing, linear equations. That's what they were learning. Linear equations, I'm guessing, in one variable. I didn't ask him that. That's what it meant to solve a problem. You provide me input, and I will give you a formula that you can plug this input in and get your answer. Right? The formula typically will be some function, x plus y plus z the whole squared or whatever, and you plug your input data into that formula and you get an answer out, right? That's what it meant to solve a problem for a long time, certainly when we were in school. More recently, what solving a problem has meant is to provide an algorithm, a procedure that you can use that can be quite elaborate to solve a problem. And this change in thinking with going from a closed form expression to an algorithm has really been radical. This is really what has enabled advances in optimization applications, but also advances from many other areas of math to science and engineering, that we think algorithmically. Okay? So what kinds of algorithms? Early on, the kinds of algorithms that were provided for solving problems were solutions of linear systems. Ax equals b. You would use Gaussian elimination, least squares, other things. Then the kinds of algorithmic procedures that were provided were solutions of eigenvalue problems. Ax equals lambda x. I give you a, can you find me x and lambda? Okay? And sort of most recently in this evolution, the kinds of algorithmic procedures that we describe are solutions of optimization problems. Okay? And a big sort of intellectual milestone that has happened in many, many domains, and we'll see some examples in the next slide, is that a problem is now viewed as solved if I can formulate a solution for that problem as an optimization problem. So you hand me something that you wish to solve, we'll see some examples. And if I can write down the solution of that problem abstractly as the solution of an optimization problem, I am done. I don't need to describe for you all of the steps involved in solving that optimization problem. So even providing an algorithmic procedure, the nature of that has changed. I don't need to give you all the steps involved in solving an optimization problem. It may run into many thousands of lines of code, but I can simply hand you the problem I wish to solve. You want to find Nash equilibrium in a game, you want to fit a statistical model to some data, you want to identify an optimal portfolio to divide your investment across a bunch of assets. For all of these things, I can provide an optimization problem for you that you can solve and get an answer for yourself. And it's a very different way of thinking about solving problems compared to the traditional approach of you give me numbers, I plug them into a formula, and I give you back the output, right? So it's in this sense that we should view optimization. So one of the examples, prominent example, how many people here, by the way, go into finance after getting a PhD? Typically, 1/3? 1/2? Less, more?
Maybe 1/4.
Okay, yeah. It's about that number or more even in the US. But yeah, this is a big application for those of you who are financially inclined for optimization ideas. An individual by the name Markowitz won a Nobel Prize in economics for initiating this field. And this is the problem of portfolio design. I give you $1 or $100 to invest. You have a collection of assets, and I want for you to design the optimal strategy, meaning the optimal way to split those $100 across these assets. In addition, I give you information about how different assets, what the expected return might be, what the risk might be for each asset. And then you can actually write down an optimization problem to solve the portfolio selection problem. I don't give you all of these steps. It's very complicated to describe to actually design the optimal portfolio. I just give you the formulation of how to design the optimal portfolio. Okay? So that's a paradigm shift in how we think about these things. In data science, you're given data observed in the context of an experiment. a class of statistical models, and you want to identify the model that best fits the data. Again, very complicated to describe the map from data and models to the optimal model, but I can simply write down an optimization problem that solves this question, run it on a computer, and that's it. So it's a very algorithmic way of thinking. I don't need to describe for you the precise map from input to output, just a formulation, and there's existing software to solve these kinds of problems. Okay? And you see this in many, many other areas, in electrical engineering and logistics. Big use case for optimization methodology is actually in logistics. So deep learning or what have you are not the most popular uses of optimization in industry. The industry that uses optimization methodology sort of in a very much more critical way than machine learning is actually logistics and supply chain. Okay? There are problems in mechanical engineering and so forth as well. Okay, so let's become a little bit more mathematical. If we had to go from the dictionary definition of optimization to an actual mathematical description of an optimization problem, you would write down something like this. Right? I want to maximize some function f subject to my vector x lying in a set S. F is my objective function. This is what I want to maximize. That's the terminology that's used. S is the constraint set, the set of points in which, from which I have to make a selection. And this variable x, the thing that I'm trying to decide to set its optimal value, is called the decision variable. It's the thing that I'm trying to decide what to set its values to so that you solve this problem. Okay? Up to here, I claim any of us would have written without knowing any optimization. Right? This is, I had a dictionary definition of it, then I have a math definition of it. This is the easy to write down for anybody. Okay? So what are questions we can ask about this mathematical description? In general, as written here, I can write down an arbitrary function and an arbitrary set. Right? So a first question is there a sort of canonical or special form for all optimization problems?
So you mean you want to pose the optimization problem?
No, I'm saying you can write any optimization problem looks like this, right? You can write down an arbitrary objective and an arbitrary set. The first question I'm asking is there a standard form, if you will, in which you can put all optimization problems? In principle, I could write any function here that can look messy, any constraint set that can look messy. Is there a standard canonical form into which I can put any optimization problem that you have? Right? Second question, sort of building off of the first question, is which problems can be solved efficiently? If I'm going to hand a formulation like this to somebody and say, hey, look, you wanted to solve portfolio design, here is an optimization problem that you can solve to get the optimal portfolio, it better be that that problem that I hand them to solve is actually easy to solve, right? So this also matters, the second one. But it really is derivative of the first question. Can we understand all optimization problems in some systematic, unified way? Okay? And I claim that there's a simple way to understand every optimization problem that you'll ever see, any standard way. And that's what this talk is about. And so one of the core messages that I want to convey in this talk is that this class of problems called convex optimization problems is a canonical form or a special class that you can put all optimization problems into. Okay? So some of you raised your hands for when you had seen, when I asked who of us have seen convex optimization, right? Please raise your hands again. How many of you were taught that all optimization problems are convex? Nobody, right? It turns out that that's true, in a way that's both useful and useless. Okay? If everything is something, then that something is not going to be very useful, right? So in a very specific way, the fact that I'm saying that all optimization problems are convex and can be reformulated as being convex, and we'll see what that means. That's very useful, it's very illuminating from one perspective. It means that if you understand convex things, you can somehow understand everything. But from another perspective, it's not very helpful because we know that there are optimization problems out there that are not easy to solve. So if I'm telling you that everything can be reformulated as a convex thing, presumably there are some convex things that are not easy to solve, right? So we do need to make a distinction between that first statement at a mathematical or conceptual level and at an algorithmic or computational level. Okay? We'll talk briefly about algorithms for convex optimization, not in the sense of actual algorithms, but in the sense of what it takes for one to be able to develop algorithms for convex optimization. What are the key conceptual pictures? And lastly, I'll very briefly touch upon two prominent classes of optimization problems that go by the names linear programming and semi-definite programming. Okay? And in some sense, progress in these areas has actually driven application of optimization in many, many other areas. Linear programming goes back now sort of to the 40s, 1940s, 50s. Semi-definite programming is a bit more recent. In its modern form, it was sort of articulated in the 70s or 80s, if you will. But you can see examples of it even a little bit before. But this is the agenda for today. Very tutorial in nature, like I said. So please stop me if there's anything that doesn't make sense. The next two lectures will be about more sort of contemporary cutting edge research. But this is background for the next two things. Okay? All right, first bit of mathematics. The optimization problem that I wrote down 2 slides ago, right? I said all optimization problems look like this, right? Can be reformulated as this. So instead of maximizing f of x, subject to x lying in a constraint set S, I can maximize a scalar t subject to x lying in the constraint set S and f of x being bigger than or equal to t. Are we happy with this? Right? I can always do this. Here, my decision variable x lived in Rn, right? That's what we said a few slides ago. Here, my decision variable lives in Rn plus 1. I've added one extra variable, and I can do this. What's the benefit of doing this? What did I gain by doing this? Sorry? Who said that? Sorry? Yes? The domain here, the constraint set S could be anything. There need not be anything convex or anything special even about the constraint set, right?
Objective becomes linear.
Good. So I started with an arbitrary objective function. F could be anything. Here, the objective function is a linear function of the vector x comma t. Good. It's a trivial reformulation, but being able to write down a linear objective is for free. So where we previously started with an arbitrary objective function and an arbitrary constraint set, I can restrict my attention to problems with a linear objective and an arbitrary constraint set. Good? So that's the main lesson here, that without loss of generality, whatever optimization problem you hand me, I can perform the simple reformulation and hand back to you a problem with a linear objective. Cool. Okay. The next slide has a little bit of math, more than this. We'll go through it slowly. So it's the first definition of the talk. It is not the definition of a convex set, which is one of the central definitions in convex optimization. It's of a related concept just concerning sets in Rn. So if you give me any set in Rn, the convex hull of the set is defined as follows. Let's go through it carefully. It's a linear combination of xi's in S. So it's a linear combination of things in S, but where the weights are very special. Linear combination we all know from linear algebra, right? That's how everybody's hands go up about linear algebra, so we know that from linear algebra. Okay. The weights, though, the lambda i's, have to be non-negative and sum up to 1. So such combinations are called convex combinations, and the convex hull of a set is all possible convex combinations of elements from that set. So if I have these 4 points in R2, the convex hull is what? Simply the square, right? If instead of those 4 points that I had originally, I have a 5th point, does the convex hull change? No, right? Good. One technicality to notice about this definition is that I am only going to allow convex combinations of finitely many things from S. So you give me a set S, S can have infinitely many elements, that's fine. But when I define convex combinations, I'm going to take finitely many things from S, take weights that sum up to 1 and that are non-negative, and that's a convex combination. So the K here is always a finite quantity. I can take 1 thing, 2 things, 3 things, that's all fine, but it's always going to be finite. Okay? Questions about this definition? Okay? Okay. The first result for today, and in some sense the only result for today, is this one. If you give me any set in Rn and any vector in Rn, maximizing A transpose X subject to S, X being in S, will give you the same value as maximizing A transpose X subject to X being in the convex hull of S. How many of us know what sup or supremum means? Good, right? It's morally the same as maximum. Think of it that way if you've not seen it before. If you've seen it, you know why it's needed. But it really is maximizing. So I want to maximize this function over all points in S. And I'm telling you that the optimal value that I'm going to get by doing that is the same as maximizing that same linear function, but over the convex hull of S. S can be anything, A can be any vector. Okay? So with the qualifier that sup we're going to think of as the same as max, right? We'll do the proof, or at least an informal proof, quickly on the board. Okay? First question is, anytime you want to prove an equality, what's a good strategy to doing this? One side is less than or equal to and the other side is less than or equal. That's it, right? Is it obvious somehow that one of these sides is less than or equal to the other side?
Supremum of A transpose X would be less than or equal to X, when X belongs to convex hull.
Right? The claim is that this side should give you a value that's less than or equal to this side. Why is that? Because, yeah, same objective function, the set on the right-hand side is bigger, right? And so I'm maximizing over a bigger set, and so, this we can assert that the left-hand side is less than or equal to the right-hand side. Are people that side able to see? I can move this up. It's not a... We now want to prove that the right-hand side is less than or equal to the left-hand side. Okay. That's, if we do that, we're done, right? So, we want to show that right-hand side is less than or equal to the left-hand side. Okay. Proof. I'm going to change the marker. Okay. Fix any z in the convex hull of S. Pick any point, fix it. What do we know about z because it's in the convex hull of S? We know that z can be expressed as a convex combination of things in S, right? That's this. Good. Therefore, good, A transpose Z is equal to A transpose that sum. What's the next step?
A transpose can be taken as A.
Surely, yes. And then, these are a bunch of what kinds of numbers?
Scalars.
Real numbers. The lambda i's are weights that are non-negative and sum up to 1. So I can say that this is less than or equal to the maximum of I from 1 to k of A transpose xi, right? There are finitely many things here. These are weights that add up to 1 and are non-negative. And I can say this. So for any point in the convex hull of S that you give me, I can hand you back a point in S that has larger objective value. So we have shown that the right-hand side is less than or equal to the left-hand side. Good. So we had previously shown that for any optimization problem, without loss of generality, I can take the objective function to be linear, right? Now I'm showing you that for problems with a linear objective, no matter what the constraint set is, S can be anything, I can always replace the constraint set by the convex hull of the constraint set. Good. And this is a picture. I have some set S in R2, doesn't need to look, I just drew something. I can go in the direction A, and optimizing A transpose X over all X and S is equivalent to optimizing A transpose X over this red area. That's what we proved on the board. Right? So here is a definition of a convex set that is motivated by the development we've taken so far. It's a little bit different than the usual definition of a convex set that you might see in a text, but it's equivalent. A set that is equal to its convex hull is called a convex set. How many of us have seen the definition of a convex set before? Good. Those of us who have seen the definition of a convex set. If you've not seen the definition of a convex set, here it is. Right? This is perfectly reasonable. But if you have, it's a good exercise to check that this is equivalent to what you learned before, if this is not the way it was defined before. So if I hand you a set S, and when you compute its convex hull, those two things are the same, then that set S is called a convex set. And so we arrive somehow at this canonical or standard form for optimization problems, namely that of optimizing a linear function over a convex set. First, our reduction was to go from any objective to a linear objective. Our second reduction, based on this previous proposition, was when I have a linear objective, I can go from any set to a convex set. Right? The definition of a convex set being this. I can replace that set by its convex hull, and once I've replaced it by its convex hull, the convex hull is by definition a convex set. Good? So, in 10 slides, we have shown that any optimization problem can be written in this way. And these problems are called convex optimization problems, convex programs, whatever. Yes, there's a question?
Before we proceed further, can
Yeah.
you explain why that objective function is linear?
Why it is linear?
Yes.
Which one?
After you made the modification f of x greater than or equal to t.
You mean right here?
Yes.
Okay. This is simply a vector with 0 in the first n locations and a 1 in the last location, transpose x t. Are you happy with that? And anytime I write something like this, it's a linear function of x and t, right? So in 10 slides, we showed that anything you would write down, any optimization problem, any objective function, any constraint set, can be reformulated as a convex optimization problem. And a convex optimization problem is one in which we maximize a linear function over a convex set. And a convex set is one where when you take its convex hull, you get the set back. Okay? These are called convex programs. They go by the name convex optimization. You have 1,000 different equivalent formalisms for a convex program in any text you might open up. And it really provides an important conceptual framework. If all problems can be put in this form, then it's a really powerful framework to reason about optimization problems in general. So if you want to study any optimization problem, in principle, you could restrict your study to this class of problems. Right? Okay, but there is a caveat. Can you use this two-stage technique? Step 1 being transform to a linear objective, step 2 being write down the convex hull of the constraint set, and then you're done. Can you use this to actually solve convex optimization problems? Can you do this in general? Even if you've never heard of the term convex optimization, your first instinct should be to say no, right? If all problems can be put in this form, I know that arbitrary problems cannot be solved efficiently, so certainly not all convex optimization problems should be possible to solve efficiently, right? How many of us know of NP, NP-complete, things like this from CS, right? So canonical NP-complete problems, things like max cut and so on, they're not as stated convex optimization problems, but using all of the tricks that I just described, you can rewrite max cut or traveling salesman or any of these other things that are favorite NP-hard or NP-complete problems as convex optimization problems, using the same trick that I just described. which must mean that there are convex optimization problems that are NP complete or NP hard to solve in general, right? Yes?
So can you always compute convex cells? Not efficiently, but with less exponential time. Sets could be infinite, for example, yes? Or
So it really depends on how the set S is presented to you. That's a huge part of, it's something that we'll sort of touch upon today. But a big part of optimization is, how is a problem presented to you? I can describe any set, convex or not, in many different ways, and how it's presented to you plays a big role in whether or not I can compute with that set efficiently, plays a big role in whether or not I can compute its convex hull efficiently, and so forth. And so the answer is in general no. Like, you can write down, I think, sets that are given by fractals and so on, where it's hard. The set S is, the set of all points in some Koch curve or something like this, right? How is that presented to you plays a big role in whether you can even compute it. So non-computability issues definitely can show up here in the absolute worst case. Yes. Yeah. Are all other formulations? You mean this one? So what I mean is that how many of us have seen textbooks on convex optimization? If you open up those textbooks, you raised your hand. If you open up some of those other textbooks, they may not describe convex optimization as this class of problems. They may have some other definition for it, but all of them are equivalent to what I've just described. So that's really what I mean. Yeah. All right. So this, of course, I've proven to you that all you need is convex optimization in some sense. This is all. Yes?
So, for this equivalence, we must be able to retype the solution of original problem from the solution of convex problem. Solving the convex problem, you get a fitting convex hull of S.
Correct.
What is the point in that? May not be in S.
In general, it need not be an S.
How do I get the point in S that leads to the same objective?
Good question. So in general, the question is, if I solve my problem of optimizing a linear function over the convex hull of S, I might get a solution that is in the convex hull of S, but not in S. But if you give me that point in the convex hull of S, it can be expressed as a convex combination of things in S. And one of those things in S, in fact, it'll turn out that all of those things in S will be optimal solutions for the problem with respect to S. So that is, in general, true. So if you can me a set S and then I compute its convex hull, if I have a way, given any point in the convex hull of S, to write down all of the points in S that I can use to obtain a convex combination for that point in the convex hull of S, then yes, I can. So all of this I'm sort of putting under this umbrella of computing the convex hull. What does it mean to be able to compute it? And so yes, we need to be able to do that. Yeah. Good question. Okay.
So is it possible to characterize convex hulls that can be computed efficiently?
Good question. It really depends on what primitives you're allowing yourself. And we will see some examples of this. So, one sort of picture to keep in mind is if I had to email a convex set to you. This is not my formulation, this is somebody else's, but it's a very useful one. If I had to email a convex set to you, how would I email a convex set to you? In general, if I'd email anything to you, for you to understand it, we have to be speaking some common language. And language is made up of some primitives, etc., and so forth. Same way with convex hulls or with convex sets. We need to agree upon a set of primitives to describe convex sets. And then I could send you an email saying, okay, the set I'm interested in is efficiently described using these primitives. So let me give you one example that's a taste of what is to come. Do we all agree that the ball in R2 is a convex set? Right? Good. If the set of primitives I'm allowed to use to describe the set only involves linear inequalities, what can a linear inequality describe? Linear function, things on one side of a linear function, right? I can use two linear inequalities to describe sets that are at the intersection of each of those linear inequalities. So if the primitives that I'm allowing ourselves, to communicate about the Euclidean ball are only linear inequalities, you need infinitely many linear inequalities to get this, right? So it's not going to be efficient. So the set of things you can describe is very much a function of what primitives you allow yourself to use. And we'll see as we get to the end, the linear programming, which only allows you primitives given by linear inequalities, is insufficient to describe this, but semi-definite programming is sufficient to describe this. So it really is a function of what language, what primitives, what building blocks you could use. Yeah? Yeah?
So, in the initial objective function, the x was belonging to the constraint set S. When we reformulated it, so it's a like AND operation of two, like x belongs to S and fx such that.
Yeah, it's x comma t such that x belongs to S and f of x is bigger than or equal to t. Yes.
Should we not be computing the convex cell of that?
Of that joint thing, yes. But yes, that's right. So I'm assuming that this set S absorbs all of the information about the function, everything. So yes, that's right. So the big caveat we were left with is we need to be able to deal with convex hulls efficiently, right? But at least I've convinced you that optimizing a linear function over a convex set is all we need. So what does it take for a convex program to be efficient? At a minimum, the linear objective function seems easy, right? Not a big deal. The key object in a convex program is the constraint set, right? And it's a convex constraint set. And so the key question is, how do you access or describe that set? It is derived from the convex hull of something. That could be one kind of way to state it. But in general, we need some way to access or describe the set. How would you access or describe any set? At a minimum, what do I need about any set to be able to describe the set? Huh? Sorry? I couldn't hear it.
Elements of the set.
Elements of the set, right? There could be infinitely many of them, right? Sorry, could you speak up, please? I'm not able to. Good. Some way of checking, sort of related to what you were saying too. If you hand me an element, is it in the set or not in the set? At an absolute minimum, I need that, right? It turns out that, so need a way of checking whether a given point is in the set or not. It turns out that with convex sets, something very special happens. That in addition to being able to tell you whether or not a point belongs in a convex set, I can actually certify this fact. Okay? And the word certify is a very important one in optimization in general, but in convex optimization in particular. It is what makes convex. So the reduction that I just gave in the first 10 slides is one interesting reason for convex optimization. The interesting reason for convex optimization is that you have this notion of a certificate that tells you whether a point is in the set or not. To get to this notion of a certificate, or to get to what this means in the context of convex sets, I want to first talk about what it means to certify something. I've used this word certify. What does it mean? And we'll do this with an example. So consider a system of linear equations. Ax equals b. A is a matrix, b is a vector. We've all seen this, right? How do I certify to you that there exists a solution? Anybody? Yeah? You could hand me a solution, right? So if you wanted to certify to me that Ax equals b has a solution, you could hand me some x hat, and I could check for myself by multiplying the matrix A with the vector that you gave me and check that it's equal to b. Good? So that's key about a certificate. You hand me something that I can use to check for myself. Good? How do we certify that there exists no solution? We all claimed we knew linear algebra, right? I also claimed that I knew linear algebra at some point, but I didn't understand it till I understood the answer to this question. How can you convince me? How can you hand me something? Just like with the case of a solution, how can you hand me something so I can convince myself that there is no solution to Ax equals b?
B does not belong in the row space of X or column space of A.
Okay, b does not belong in the column space of A. So suppose I hand you A and B, you tell me b does not belong in the column space of A. Why should I believe you? With the previous case, what he said, right? He handed me a solution that I was able to check for myself, right? If you tell me b does not belong in the column space of A, why should I believe you? Just saying something is not the same thing as certifying that thing, right? So how would you certify for me that this thing is no solution?
You see the span.
Sorry?
You see the span of the matrix A.
Okay, and?
B does not belong to that span.
How would you convince me of that fact? You can tell me that. How can you hand me something where I can check for myself that that's true? There was another idea back there, right?
Using combination of columns of A, if B does not belong to that, then actually this equation is saying the same thing.
That's the same as what he was saying, that B is not in the column span of A. Good, but that's not convincing me of it, right? How can you hand me something where I'm left in no doubt? Yes?
Rank of A augment B should be more than rank of A.
Okay, why should I believe your computation of the rank of A and rank of A augmented with B? Right? I still have to check all of those things, right?
You can perform elementary matrix operation on both the sides to
But that's going through the process of solving the problem, right? Is there something simpler than solving this, where you can hand me something where I can convince myself that this is no solution? Yeah?
projection of B into the space of A.
Okay, so you project B onto the column space of A. Why should I believe that the projection that you handed me is in fact the projection of B onto the column space of A? I still have to check your computation, right? If I really have to believe this, right? But is the issue clear? Yes?
Even these are y such that A transpose y is positive, let's say greater than equal to 0, and B transpose y is negative.
And that's exactly what we will do. That's Farkas lemma. Someone who knows about Farkas lemma, you'd answer this. But you don't need to go as far as Farkas lemma, which involves linear programming, to assert something much more elementary in linear algebra. Okay? So if I could hand you a mu such that A transpose mu equals 0, and B transpose mu equals 1, you can check for yourself using that mu that there is no solution. And it goes as a proof by contradiction. Suppose I hand you such a mu, right? And you come along and say, oh, maybe there is some x hat that is a solution. Well, Ax hat, your claimed solution, this is your claimed solution, transpose mu, is equal to x hat transpose A transpose mu, that equals 0, right? Because A transpose mu equals 0. Good. And B transpose mu equals 1. So any x hat you claim as a potential solution, that is contradicted by the existence of such a mu. So if I hand you such a mu, that's a certificate of the fact that there is no solution to the system of equations. And the reason it's a certificate is if I hand you a mu, you can check these conditions for yourself. Right? I hand you a mu, you can multiply A transpose by mu and check that it equals 0. You can multiply B transpose and mu and check that it equals 1. You don't need to believe me, right? You don't need to believe a rank thing, a projection, column space, none of that stuff. You can check this for yourself. So this is what it means to certify something. You should not care how I came up with the mu. Right? Just like with this case, you don't care how I came up with a solution that I produced for you as a certificate. Right? It doesn't matter. That solution itself is enough to certify some fact. Same way here, a mu that I can hand you, you can check these conditions for yourself, and that's enough to certify that there is no solution. And there is a famous result in linear algebra. It actually can be stated in infinite dimensions and so forth. But it states that the converse is also true, meaning that if the system, so we know that if there exists such a mu, then this is no solutions. But Fredholm's alternative asserts the converse also, which is that if this thing has no solutions, then there will always exist such a mu. So I want us to understand this example, this in particular, geometrically, because that's what we will need as we go to the next stage, where we go back to convex optimization and connect with all of those things. Okay? I have written down a set in RD. What kind of a set is this? It's a collection of points in RD. It's a solution of one linear equation. What kind of, if you think about it geometrically, what kind of set in RD does this describe? A hyperplane, right? The solution of one linear equation is a hyperplane. The point B belongs in RD. So this is a hyperplane. This is my hyperplane. The point B, because B transpose mu equals 1, let's assume that we're living in this regime where there exists no solution, B transpose mu equals 1. This is the set of points which, when I take a transpose with mu, equal 1/2. Okay? So B is not going to be in this hyperplane, right? B will be somewhere here. I have another set, which is the image of A. People use the word the image or the column space. That's what this is, right? Where does this set live? Which space? RD also, right? Just dimension check. If that system has no solution, I've told you that there always exists a mu such that this is true. I'm using that mu to define my hyperplane. What do I know about the column space of A in this picture? This is all points that when transposed with mu give me 1/2. B when transposed with mu gives me 1. What about things in the image of A? What will they give me when I transpose them with mu? 0. So this set, which is the image, well, I shouldn't draw a 2D thing, a 1D thing, might lie somewhere here and it has the origin in it, right? So what this hyperplane is doing is that it takes the fact that B is not in the image of A, B is not in the image of A, and sticks a hyperplane in between those two things. What's true about a hyperplane? What's true about a hyperplane is that it breaks Euclidean space into two distinct pieces. One side and the other side. Okay? Yes?
So you would have always done this with other numbers, right? I mean, not just 0 or 1.
Certainly, yes. I could have said 0 here and anything else here, and I need not have put 1/2 here. I could have put any scalar strictly between 0 and 1. Sure, yeah. But what this whole thing is saying, again, living in the situation where there exists no solution means that the image of A and B are different sets. What it means is that there exists a mu such that this thing is true, but how to interpret that mu is to say, well, let it define a hyperplane. B is going to lie on one side of the hyperplane, and the image of A is going to lie on the other side of that hyperplane. So this certificate, this mu that I'm handing you, explicitly can be viewed as a way geometrically to split B from the image of A. Okay? And this picture really is one of the, even though it can be understood purely in a linear algebra context, is really the key picture in convex optimization too. Okay? So there's a famous theorem called the Hahn-Banach theorem. We're not going to prove this, which says that if I have a convex set that is closed and bounded, if you've taken analysis, closed and bounded means compact. For any z that is not in my convex set, there exists an A such that this is true. So what it's saying is that if I have a convex set C, I have a point Z that is not in the convex set. What's the picture corresponding to this theorem? That there exists a hyperplane with the normal vector of that hyperplane given by A that separates the convex set from Z. So I have an explicit certificate. I can actually have, if you give me a convex set C and you give me a point Z that is not in C, I can certify for you the fact that Z is not in C by providing a hyperplane that will separate C from Z. So not only am I telling you, well, Z is not in C, I'm explicitly giving you a hyperplane that certifies that fact. And it certifies it geometrically in this way. Okay? So this is what is special about convex optimization. Let's draw a set that is not convex. Would this theorem break? For what points would it break? I could put a Z in here, right? You have no way of separating that Z from the rest of C using a hyperplane. And so this object called a convex set that we arrived at from purely optimization considerations has a different way to arrive at convex sets is from this perspective, which is to say, what's the class of sets where hyperplanes work to separate points that do not belong in the set? And that's another way to define convex sets. Okay. What about points being in the set? That's a way to exclude things from being in the set, right? What about points being in the set? Here I need a modest definition. Fix a convex set C. A point Z in C is called an extreme point of C if it cannot be expressed as a convex combination of other points in C. So let's again draw pictures. I have a convex set. Which points in this convex set are extreme points of the convex set? The four corners, right? If you pick any one of them, let's take this one for example, it cannot be written as a convex combination of other things in C. And anything inside can, right? What about the Euclidean ball? What are the extreme points here? All the points in the boundary, the sphere, right? Is it the case that boundary points of this box are all boundary points are extreme points? No, right? So points here are expressible as convex combinations of that and that. So it's not the case that boundary points are extreme points always. Sometimes they are, sometimes they're not. So there's again famous theorems. These can also be stated in infinite dimensions, at least the first bullet point can, not the second one. But if you start with a convex set that is closed and bounded, then we have that C is equal to the convex hull of its extreme points. So I can simply take extreme points, take their convex hull, and get you to C. And every point in C is a convex combination of at most dimension plus one extreme points. Okay? These are two sets in R2. Is the set convex, closed, and bounded? Yes. Is it equal to the convex hull of its extreme points? Yes, it is, right? I can take these 4 points, take their convex hull, and I get the box back. Same thing with the ball too. The extreme points are just the sphere, the boundary. I can take their convex hull and get you back the ball. Okay. If I want to express any point inside, say this one, how many extreme points do I need to express that x? 3? Which 3? I could use this, this, and this. Or I could use this, this, and this. It's not necessarily unique, but both of them work. Does that agree with this theorem? Yes, it does, because 3 is 2 plus 1. What about here? How many do I need to express any point inside? 2. Right? What if I took the Euclidean ball in RD, not in Rn, not just in R2? Even though the theorem says d plus 1, for the Euclidean ball, 2 always works, right? Good. And so if I wanted to convince you that this x belongs inside the box, one way to do it is to explicitly give you this, this, and this, and the weights, and that'll certify for you that this x belongs in the box. Right? So for each x that you hand me, I can provide you the extreme points and the weights, I can give you the explicit convex combination, and you can check for yourself. Same way here. I can give you the points and the boundary of the ball. You should not care how I found them, but if I just give you to them, give them to you, we're done, right? So the notion of a certificate still applies here too. Okay, so Yes?
So for the point two, right, you sort of need the set of all extreme points, which may be infinite.
Could be infinite, yes. So what's the question?
That is still not like a good set, right? Because I couldn't even store all this.
You could not store, but you could check, you could check in a finite way on a computer using an algorithm that a given point is an extreme point, right? So for the Euclidean ball, you could check for yourself that a given point has Euclidean norm equal to 1. You can check that for yourself.
There's a lot of checks, right? Because you don't say which n plus 1, right? And you have infinitely many extreme points. Let's say on the circle, right? I can check if a point is an extreme point or not. On the circle, let's stick with circle.
Yeah, let's take that,
I
yes.
don't know which extreme point, and then I have to take all possible and check which ones.
No, so the thing with the disk is that we both agree what the extreme points are, right? And we both agree that checking whether something is an extreme point is easy, right? Good. You hand me a point, x, and you ask me, does this lie inside the disk or not? I come back to you and tell you, yes, it lies in the disk. And here is the explicit certificate of that fact. I express x as a convex combination of two things. You have to check, A, that those two things that I handed you are extreme points, which we both agreed was easy. B,
If you give it something, if you give me which 2 points, then it's.
yes. So for now, I'm not telling you that it's easy to find or hard to find. In general, we should not expect this to be easy to find, right? Because I told you that all optimization problems are convex. So these things should not always be easy. But the distinction isn't finite versus infinite. There are finite things too, where if the list of extreme points is exponentially large, you're out of luck. So we have to be careful about, whereas the Euclidean ball is always easy even though it has infinitely many extreme points. So the point is, in what form do we have access to the set? But yes, that's definitely a very much valid point. So I claimed in the previous slide to really say I'm going to deal with algorithms. I didn't really deal with algorithms. But we have a sense of what makes convex things special and what you might need to solve a convex problem. As that question that was just asked suggests, we know with convex sets, we have nice ways to exclude a point from being in the set and to certify a point as being in the set. But we still need to do those things efficiently. Just because we have access to these concepts doesn't mean that we can always do that efficiently, right? And so when is convex optimization easy? Informally, it's when this whole certification process of including and excluding a point in a set is easy. So if I have an efficient way to anytime you give me a point not in the set to produce a hyperplane, if I have an efficient way to do this, that counts for efficient exclusion. And if I have an efficient way to certify a point as being in the set by producing extreme points, convex combinations, and so forth, that counts for efficient inclusion. So convex optimization is easy. Informally, there's lots of theory surrounding this when this is true. And this isn't in direct correspondence with finitely many extreme points, infinitely many, and so forth. It just is a feature of the particular sets that you might have. Okay? So if we can do this easily, convex optimization is easy. And exactly these principles are used in tons of algorithms. The ellipsoid method you might have heard of, interior point methods, projectors, all of these methods and many others can be interpreted as using these facts. Okay? So, rather than sort of describing all situations when convex optimization is easy, in the last sort of 10 minutes, I'll touch upon 2 examples. Linear programming and semi-definite programming. These are both special cases of a much broader class of problems called cone programs. If you're interested, I can talk about cone programs offline. But let's just stick with linear and semi-definite for now. Okay? Okay. To describe linear programming, we need one definition. So again, when I've told so far, if I come after all the first 16 slides, the only question of interest somehow, at least in this perspective, in this story, is sets, right? Because the objective function is always going to be linear. So the question you should ask, or you should be thinking in your mind when I tell you, hey, I'm going to tell you about linear programming or about semi-definite programming, the question you should ask is, what kinds of sets can be described using linear programming? What kinds of sets can be described using semi-definite programming? That should be sort of immediately the direction or question that you gravitate to, right? Because that's really the only object of interest here. So with linear programming, a polyhedron in Rn is a set that is described this way. All points in Rn such that Ax plus b is bigger than or equal to 0. A is a matrix, b is a vector, and so this affine function of x should be greater than or equal to 0. This thing, Ax plus b, will spit out a vector in Rd, and when I say bigger than or equal to 0, I want every entry of it to be bigger than or equal to 0. Such sets are called polyhedra. If d were equal to 1, what kind of set are you getting? You get something called a half space, a single linear inequality. When d equals 2, you get the intersection of two things, and so forth. So you have the intersection of d, what are called half spaces. That's what describes a polyhedron. Okay? Polyhedra are convex sets. The way I've drawn it, it should be evident, but this is something you can check for yourself. And linear programming is the optimization of linear functions over polyhedra. So linear functions, linear objective functions in the constraint set is a polyhedron. So to answer the question that was asked earlier about which convex constraint sets are easy, let's turn it around now and ask, I'm allowing you to use half spaces. Can you describe the set you care about in terms of half spaces in an efficient way? Right? So you pick a primitive first, and then you ask what can be described efficiently using that primitive. And linear programming, informally speaking, is efficient if d, the number of half spaces, is a polynomial function of n. So if this is true, then you'll be able to solve a linear program. Again, informally speaking, I'm not writing a theorem here. In time complexity, that's polynomial in n. N is where the original problem is stated. Okay? All right. So what sets can be described using linear programming? So the L infinity ball is all vectors where the maximum entry in magnitude is less than or equal to 1. If you've heard of the L infinity norm, this should be natural. If you've not seen it, this is the definition. If I'm only allowing myself half spaces or linear inequalities, how can I, is this set, by the way, as written, is it described in terms of half spaces? No, right? There's an absolute value function, right? How can I write it exclusively in terms of half spaces? Any ideas? Sorry? You have to speak up. I can't hear you.
X1 should be greater than equal to minus 1. X should be less than equal to 1.
Perfect, right? So the suggestion is that I have this. This is explicitly in terms of linear inequalities. How many linear inequalities? 2n, right? For a set in Rn, I'm using 2n linear inequalities and I have it. The simplex is an interesting example. I would suggest working it out as an exercise. But let's do something slightly more interesting. If this is, again, the unit ball of the L1 norm, if you've seen it. If you've not seen it, this is the definition of the L1 ball. The sum of the absolute values of my entries has to be less than or equal to 1. Is this described in terms of linear inequalities? No, there are absolute values here. Could you use linear inequalities to describe it? I see a bunch of people nodding. Can you give me a description in terms of linear inequalities? Sorry? What is that?
1 transpose X.
Less than or equal to 1? Is that enough? No? Yeah.
Not just 1 transpose X. So that vector 1, it should be all 1s and minuses.
Good. So, a way to describe it in terms of linear inequalities is to take all possible signs here in front of the xi's and get less than or equal to 1 for all possible signs here. Okay? How many linear inequalities is this? 2 to the n linear inequalities, right? Is that good? Feels suboptimal, obviously, right? Can we do better? It turns out that in Rn, if you have to describe the set only using linear inequalities, you cannot do better because it does have 2 to the n active linear inequalities. So, in Rn, describing the set requires exponentially many linear inequalities. But a magical fact, that's true, I've known it for 10 plus years, it still is magical to me, is that this set can be expressed as the projection of a set in R2n, the original n variables and n more variables, n extra variables that I've added. And in R2n, these are the inequalities that I have. And these y's are explicitly accounting for the absolute value stuff here. And so I have this object in R2n. Is this object in R2n a polyhedron? Yes, it's described using linear inequalities. How many linear inequalities? 2n plus 1, right? 2n plus 1. Linearly many. So I added n extra variables and linearly many inequalities suffice. So this whole paradigm in optimization goes by the name lift and project. So I describe an object in Rn by lifting, going up to a higher dimensional space. As long as this higher dimensional space is a polynomial function of the original space, I'm still okay. And then I project back down. And projection gives me an immense amount of extra descriptive power, right? And so this is very, very powerful in optimization. And it's a sort of magical fact that you can get something exponentially complicated using something only linearly complicated in a slightly larger dimensional space. Semi-definite programming, in the last 2 minutes that I have, is, again, we ask what the constraint set is. The constraint set in semi-definite programming is what's called a spectrahedron. It's a set of the following form. Previously, we had ax plus b bigger than or equal to 0. We have the same ax plus b bigger than or equal to 0, but bigger than or equal to is interpreted in the matrix sense that this is positive semi-definite. Okay? So A is a linear map. Remember, previously we had ax that takes x and spits out a linear function of x. Here we have a linear map that takes a vector x and spits out a d by d symmetric matrix. That's what this stands for. B is a fixed d by d symmetric matrix. And when this thing is positive semi-definite, the set of all x's forces is PSD. This is called a spectrahedron. Spectrahedra are convex sets. There is a systematic way in which you can think of spectrahedra. Semi-definite programming is the optimization of linear functions over spectrahedra rather than polyhedra. And there's a systematic way in which semi-definite programming generalizes linear programming. So semi-definite programs are strictly more general than linear programs. All of the efficiency stuff we talked about continues to hold. I can do examples on the board, but I'd rather not because we are running out of time. This is my last slide. The one thing I'll leave you with is that lift and project is just as powerful in STP land as it is in LP land. It's somewhat less well understood with STPs compared to LPs. One suggestion of why this is complicated is that if I have a polyhedron and I project it, I continue to get a polyhedron. If I have a spectrahedron and I project it, I may not get a spectrahedron. So one popular example is if I take the cylinder in R3 and I project and I get what's called the racetrack in R2. You can imagine how you can project the cylinder from a certain direction and get this in R2. This is a spectrahedron, this is provably not. And so there are tons of such examples. Whereas with polyhedra, projecting a polyhedron always gives you a polyhedron. Okay, so this brings me to the end. There are some examples I can work out with semi-definite programming. If people are interested, we can do this offline. But convex optimization really is, in some sense, a canonical class of optimization problems. Everything can be reduced to convex optimization, but this whole paradigm is only interesting if you can compute or certify sort of points being in a convex set and not in a convex set in an efficient way. We briefly discussed linear and semi-definite programming at the end. I just want to make a note about the next 2 lectures. The second lecture was going to be about the connection between convex optimization and topics in algebra. I've decided to swap that out for connections between optimization, convex optimization, and graphs, in particular how convex optimization can be used to solve problems arising in the context of graphs and networks. So this, I hope, will be sort of broadly accessible. And the last one is pertaining to something in data science where we fit, rather than using convex sets for optimization purposes, we fit convex sets to data. Good. Thank you all. Thank you for coming.
So thank you, Venkat, for